we've got, ooh, we had some there briefly. There we go. I've got 1, 2, 3, 4, 5, 6. This is the 6th harmonic. Obviously, amplitude starts getting smaller as you go, and hopefully you can imagine that as if I were doing a much smaller string, it'd be a lot harder to get to this. Because at some point, even though mathematically we will assume that the string doesn't have any mass, at some point it does seem to affect it. So what we're going to do is predict that frequency that it took to create the 6th harmonic. Why don't we start with the 1st harmonic and work our way from there. So the 1st harmonic, the length is a half of a wave. So to get the 1st harmonic, this is going to be a half a wave right here. So I just need to figure out what that is. I'm using very precise measuring. Ideally, also the we'll keep it like that. That's 1, and so that's an additional 15. So 1.15 meters. So L in our particular case here, 1.15 meters. So if that is half of a wave, what is the wavelength? Yeah. There's a decimal point right there. So the wavelength is 2.3 meters. Not quite enough information to make a prediction of what the frequency is. Now we talked about the fact that for a transverse wave, which is what this is, for a transverse wave, the tension dictates how fast the wave is going to travel. Actually, there's 2 things which dictate. It's the tension in the string, created mainly by that 200 gram mass right there, and it is the string itself, the material. So we have an equation for the speed of a wave traveling along, in essence, a one-dimensional medium. Actually, I'm going to give you the generic first. The speed of a wave typically is some sort of force term over some sort of inertial term. And what I mean by that is the force term is how much influence does one particle exert on the one right next to it. And the inertial term, in essence, is how much mass are we trying to move. The more mass it is, the slower the wave's going to be. Specifically for something like this, the speed is equal to the tension divided by the linear density. All right, tension, simple enough. I'm just going to trust the manufacturer right now. It's a 200 gram mass sitting on the end there. If I did a force diagram of that 200 gram mass, I have weight acting down, I have tension acting up. It should be close enough to equilibrium that those 2 forces will balance. So the tension should be equal to the weight hanging. The formula for weight.
Depends where you're at.
Pardon?
Depends where you're at.
There's a general formula.
mg.
Yeah, that's what I'm going for. And so we have a mass of 0.2, is that things? So 0.2 kilograms times 9.8 is good enough for the crude approximations we're doing. So the tension of the string is 1.96 newtons. But what about the linear density? What is the linear density of the string? Well, first off, what's linear density? We'll take it back one step further. What's density?
Mass divided by volume.
Yes. So this is density, or if you need to stick something in front of it, volumetric density, general just density. If we had surface density, then that's mass divided by the area of the surface. If we're doing linear density, mass divided by what?
Distance.
Yeah, or length. Yeah. Mass divided by length. This is linear density. So if I had this string unattached, I could stick it on a balance, find the mass, get a meter stick, measure how long it is, find the linear density. Having done this enough, I'm gonna hopefully not being off by 0. In this particular case, just having done the measurements before, it's about 0.001 kilograms per meter.
So what mass do you use to get that?
The mass of the string, I take
Okay.
I take string that's from the same lot, or
Okay.
that string itself, put it on a balance, measure its length.
Okay, I just wanted to make sure it was the mass of the string.
Yeah, it's mass of string or same type of string. And we'll blame this right here. Matter of fact, in the lab, when you do the vibrating string lab, which you do, I guess, after Thanksgiving, this is the biggest place where people mess up, because the triple beam balances aren't automatically starting on 0. And so some people just, take for granted, they don't bother to zero it, don't see what the offset needs to be. And in which case, if I have a piece of string that has a mass of 0.8 grams and it's off by 0.2, then I've already introduced 25% error into the problem. So this is the place where you really need to be careful of actually getting the real measurements there, which I'm not doing right now. But it is somewhere around there, I believe. All right, so I can now predict what the speed of the wave is. So it's going to be the square root of 1.96 newtons divided by 0.001 kilograms per meter. If someone would be kind enough. Units? What did we just find? So the units are?
Is it MS?
M/S? Yeah, meters per second. All right, so I have the speed of the wave, but I'm still lacking frequency. I know the wavelength, I know the speed. I've done the new F frequency bit, right? Let's talk about the new. Looking for some look of recognition. The new.
Yeah.
I did do that, all right. So I've talked about the equation that the speed of a wave is also equal to the frequency times the wavelength. So I have two different formulas for speed. This one will, and if I were talking about the speed of sound going through air, there's still a force term and an inertial term. It's just much more complicated than this. But this is going to be true for oscillating motion. The wavelength we calculated, and it was 2.3 meters. So I have the frequency times 2.3 meters is equal to 44.27 meters per second. And so the frequency somewhere around 20.
19.25.
Units?
Seconds.
Meters per second.
No squares in it.
News.
You were closer with seconds. I see how you got seconds, but you forgot where the seconds are. All right, we're dividing both sides by 2.3 meters. So I have meters per second divided by meters, which is the same as meters per second times 1 over meters. Meters cancel out, I'm left with 1 over seconds. Otherwise known as perhaps an outdated reference on the radio of your car. What are the units of the numbers?
Hertz?
What? I think you said it.
Hertz?
Yeah, hertz. That's a hertz. On the radio, it's, I think, kilohertz and megahertz. But hertz is the base there. All right, let's find out basically how close we get. Let's see, so. Turn that on. Oh, I was doing all right. Somewhere around there. Not great, but not too much. Get stable. So close. All right. It's somewhere around there. It's not a great one, but the frequency 20.1. We predicted 19.25. Not too far off. Under 5%. Let's get to the next harmonic. I know my speed of the wave, that's not changing because I'm not changing the string, I'm not changing the mass down there. Wavelength stays the same. Oh, no, sorry, wavelength changes. So the next harmonic, L, the 1.15, is equal to the full wave. And so my next harmonic is I have 44.27, the speed of the wave based upon the tension and the density, is equal to frequency times 1.15 meters. For the second harmonic. And so the frequency would be $88.54. 44.27 divided by 1.15.
Yeah, like 38,
38.5.
38.5?
38.49, or yeah, 0.55, you round up.
Oh, okay, yep.
Yeah, that's, I was about to say.
I doubled the wrong thing. I doubled that, not that. So 38 point,
Five.
fuck, just 5. Close enough.
495.
All right. 38.5 hertz. And the second harmonic, 38.1.
Very.
Even closer. And let's do the third harmonic just to celebrate. The wavelength, I know that the length, the 1.15 meters, is 1.5 waves. So in this, excuse me. So in this particular one, I have 1.15 meters is equal to 3/2 of a wave, or 1.5 waves. Depends on if you're a fraction or a decimal fan. And so the wavelength is
I have a question.
Yes.
Kind of confused. When we did the 1.15, I thought that was supposed to be the distance of the, well, I guess.
it's the distance from here to here.
Right, and that caused us to get the second harmonic.
It's the same as the second harmonic because the second harmonic is just one wave. So the length is the wavelength.
And then how did we, when we did 2.3,
2.3 for the first harmonic, this was the first harmonic. First harmonic's a half a wave, so basically that's half of a wave.
right,
And so the full wave would be twice that.
okay, I'm with you. Okay, yeah, sorry.
All right. So now I've got 1.5 waves crammed into 1.15 meters. So what is the wavelength?
0.767.
Is that what you said?
Yeah, I rounded.
Okay, meters. So the frequency to produce that, assuming that we still keep that the same. So I now have 44.27 is equal to 0.767 times the frequency. So you get 57. 72 hertz. And just for those who can't read my handwriting. All right, so that number and that unit, those are the equals. Let's see how close we get. So get down to good stable. That does not look safe. Somewhere in there. And so the frequency, 58.7 hertz. That's the experimental and that's the theoretical. So we are, I think, just shy of 2% off. A physics demonstration that actually is under 5%. Let's pause for a celebrating. I'm celebrating insight. I'm sure all of you are as well. All right, questions to hear?
For the speed equation with the 2.3, where did you get the 2.3 from?
That's the wavelength, because I know the speed, we found the speed using that formula. The speed is also frequency times wavelength. And for the first harmonic, that was the wavelength.
Okay.
Right. All of you are now experts in the two fixed ends. I think it's time to change the game. I'm interpreting silence as joy. So a fixed end is a node. The simplest one is the first harmonic, and so forth. Now let's do two free ends. So we need to erase the word first harmonic. Two free ends. A free end is an antinode. And the simplest form that we can get there, well, I have to have an antinode on each side. That's the simplest form. How many waves is that? Yeah. So if that distance there is L, L is equal to a half of a wave. Basically, if you think of a full wave right here, all we did is just chop off the end quarters, and we're left with a half of the middle. The second harmonic, well, I start out with an antinode, I have to end with an antinode because they're both free ends. How many waves